So today we are going to start discussing Poisson and Laplace equation, the solution of this equation and its physical consequence. This follows chapter 3 in Griffiths, but the main discussions here will be actually for some cases that Griffiths does not discuss, but I'm assuming that you read Griffiths and you know everything already. So we want to discuss a bit the Poisson plus Laplace equation, and today I'm going to focus only on the Laplace equation, or mainly on the Laplace equation. So as you know, last lesson we have div E equal minus rho the charge density in space, and from here, together with the fact that the rotor of E is 0, then we can write the potential. So E is minus the potential, and then if there is no density, then we can write the Laplace equation when P is equal in a region in space where the rho, the density, is equal to 0, simply because E is given by div V. So now the question is the following question. We know that V in space in general is given by this expression, d tau rho of r minus r prime 4 pi epsilon 0. So here is the solution. If we look at the Maxwell equations, so everything is known. We know everything. So why is this not enough? Not from the point of view of solutions of particular problems. Obviously, this expression is very kind of formal. You do not understand what it means. But here is the solution. Give me the density. I'll give you the potential. And if there's some region out of with no charge, okay, so this is the solution. So what do we need to do more in a formal way? What is the problem here?
To solve this integral.
To solve this integral is the technical question that I don't care at all about at this stage. Of course, in practice, I do care about it. But here is the solution, but okay, it's complicated. I totally agree with this, and solving this is, let's say, it's also in some cases impossible, but you can do it numerically, let's say. So, as a matter of principle. Only for the Laplace equation. Okay, so let me just clarify myself a bit better. So what I'm thinking about, I have some places where rho is not equal 0, let's say here and here. But I'm looking at a place here, and I'm asking what is Vx, y, z at this point. X, y, z are some coordinates. And then, okay, here there's no charge, so in this region, delta V, the Laplacian is 0. That's what I mean. So, but what I'm trying to say here, let us look at all space, not only at one region. We have here some charges. Okay, the basic equations tell you that given these charges, I know the solution, and that's it. The issue is, why do we care so much about Laplace equation is, I'll give you a secret, we many times do not know what are the charge distribution. We have no idea. I mean, I can tell it, you know, here are some charges. Here, for example, let's say this is some object. Can you go inside this object and say what is the charge inside? You need to break the object, go inside and count the number of charges. This is in many cases impossible. So what happens in reality is that while the charge density is the truth and nothing but the truth that gives you the electric fields, that's absolutely correct based on Coulomb's law. In reality, we don't know many times what is the charge distribution, but we know other things. And what do we know in many cases? We know different boundary conditions related to the potential. So, and this is what I want to discuss. So in many problems, what we have is we don't know what is the density, but for example, we have here two objects, and I know the potential on the surface. At this stage, the potential on the surface can be extremely complicated. In practice, then I cannot solve it, but let's say I know the potential on the surface. And maybe I know here the potential on the surface. That does not imply that we know what's going inside. We know only what is going on the surface. For example, let's say I have an object which is a black box, and I want to determine experimentally what is the potential on the surface. Let's say I do it. How can I determine the potential on the surface? Again, in principle, there are several practical ways and there are in principle ways. So how do we determine this boundary condition? How do we determine it? In a laboratory, I mean. It's simple. In principle, it's simple. In practice, it can be extremely complicated. What do we need to do to find this potential? We take a test charge with charge Q. This is a test charge. And we bring it over here to this location. If I take it from here to here, what do I can in principle measure what? The work done, the amount of energy. And this will be the potential difference between here and here. Let's say at infinity, it is 0. So I bring it here, and then I know the potential here. Then I can repeat the experiment again. I take this charge and bring it here, but that will be pretty stupid. If I come here, I can already go along the surface with my test charge and determine the potential. This is not totally trivial, but it's trivial for you because you got used to it. That is, this is essentially because the rotor of E is equal 0, and then the path is not important here, so we can do this and get the potential on the surface. Okay, now I have the potential on the surface, or I measured it somehow, and now I want to solve here and here to find the potential in all space. So, by the way, mathematically, how are these type of boundary conditions called? Dirichle. So these are Dirichle boundary conditions. PC is not before Christ, it's boundary condition. It is given by, in this kind of thought experiment, given by the measurement of work, essentially, or the potential on surface. There is another type of boundary condition, which is famous, that you heard about in some other course, which is called Neumann. So what is Neumann? Neumann would say we don't know the potential on the surfaces, but what do? We do know? We know the derivative of the potential normal to the surface. Okay, that mathematicians solve these type of problems and other courses solve them, but how will we, what does this mean from a physical point of view? What do we know in this case? The field. So, the Dirichle boundary condition is the measurement of the potential on the surface, that is work. And in this kind of thought experiment, the Neumann boundary condition, which is, we know dV dN normal to the surface, so it can be extremely complicated. That is, at each point we have different directions. What do I know here? The derivative physically, you can think about a conductor, for example. What is the derivative here? It gives you the field, where the field, at each point there is a different field in principle. Then, of course, if it's complicated, we cannot solve, but in principle, I measure the field. So what do I need to measure with my test charge? Do I need to come from infinity and measure? How do I measure the field? What?
The force.
I need to measure the force somehow. We will. I don't say I know how to measure forces, but some people got Nobel Prizes on measuring forces. We will discuss this a bit later. And then what I need to do is I need to go over the surface and measure the force. Of course, saying this is very easy, but doing this might be also difficult, but because measuring the force, you need a charge. And if you need a charge, the charge itself will change the charge distribution. So when I mean measuring the force, as a theoretician at least, I mean come with a test charge with epsilon amount of charge that doesn't do anything, and then the experimentalist will say, but if it's epsilon, then I cannot measure anything. So this is assuming that there is such a limit of measuring the field around, and then I just need to do a circle here. I don't need to come from infinity, which can also be very difficult. So, okay, in practice, they will not come from infinity, they will come from some distance, things like that. Okay, so now we understand the two types of boundary condition. Now, in reality, okay, mathematicians, there are also mixed boundary conditions. So it can be that you know the potential here, you know the normal derivative here. We are not going to discuss these type of things. And actually, what we are going to usually discuss is the Dirichlet boundary conditions. And I'm not going to even teach you how to solve the Laplace equation. I'm just going to give you a physicist point of view on this type of problems. Okay, so, yeah, but now just a reminder, but what does it mean, for example, in the Dirichlet, what does it mean a constant potential? So the easiest one is, the easiest example is that the potential is constant. This is a typical example. And then if the geometry is simple enough, then usually you can solve it. So what does it mean, constant potential? Well, that means something profound. And what is the profound thing? How do you get a constant potential, let's say on a conductor? Okay, you say that you need to ground it. Ground it, for me at least, is usually V equals 0. That is true. But let's say you want this potential to be some constant compared to the 0 that it is an infinity, because these are the typical examples. What does it mean? It means something very simple. You know all this. It means you have a battery. And what does it mean if you have a battery? It means you have chemistry. In the chemistry you hide behind. The physicists don't like to discuss real chemistry. So you add a battery. The job of a battery, as a slogan at least, is to maintain a constant potential on, let's say, your conductor. And how does it actually do that? What is the battery doing in order to give us a potential? So a battery, what it does,
Potential difference.
but yeah, potential difference, but I want to make it a little bit more precise. What is the energy that is provided here? What type of energy is provided in order to maintain this charge distribution, which gives you a constant potential? So the key word is very simple. This is chemical energy. You have chemical reactions in the battery, that usual case, that provide, what do? They provide charge. So if I have several types of body and I want the same potential on these two bodies, some constant, 1 volt. For each body, I need to provide charges. This is the charges that exist in the original equation. But I don't know these charges. I don't know how they are distributed. Maybe here, on this head, up here, there are more charges. Maybe down here, there are more, less. We don't know because in general, the surface is complicated. And if it's a conductor, then okay, we know there's no field inside. We know all these general things, but we don't know the exact charge distribution. That's why the first equation was not useful. But we do know that the potential is constant. And this is done by supplying some charges, which depend, the amount of charge depend on the amount, on the geometry and all this stuff, such that the potential is kept constant on this body. And this is done by some chemical reaction. And just for you to remember this forever, because the physics of battery, which is done in our chemistry department, there are really some very nice people, professors here in Bar Ilan, that are doing beautiful battery physics, which means they give you this charge. Gedanke and I think many famous people actually, they work in the chemistry department, so you should thank them. And the physicists hide this chemistry, of course, but it's totally untrivial. So we have, for example, the simplest battery. It does a chemical reaction, Zn 2 plus 2 electrons. So this is just like some chemical reaction where you supply electrons, and you can also take the electrons. You can take electrons away, and it can be ions, it can be many things. So we have this type of reaction, and then also Cu 2 plus 2e minus goes to Cu. So maybe, I hope you know what more or less this means. The goal is not to understand it deeply. What is zinc? This is zinc. Zn is zinc. This is Cu, this is copper. And this is a particular type of battery that is not actually really used. So you have an anode and a cathode, and this anodes and cathode in a magic way can supply through this chemical interaction. This chemical interaction, the point is it gives you energy. I mean, it not gives you for free. It means you take the chemical energy, make a charge, somehow you distributed this on this surface, and this will give you a volt at a certain level. Assuming, for example, this is a conductor, by distributing some charge here in a very complicated way, in principle, if the boundary is very complicated. So this is the magic of chemistry that we hide under the carpet, but it is there, and it's not trivial at all. So now, okay, so now we have the general, very general picture of the Laplace equation. So we want to solve the Laplace equation, and then the problem becomes technical, and it was also addressed. Part of this was addressed in previous classes. For example, I don't know, in quantum mechanics, you have this Laplacian. In quantum mechanics, the Laplacian is the operator of the kinetic energy. So the equations are, of course, a bit different. But the complicated thing is usually to identify some symmetry that helps you solve the problem, and identify the boundary conditions. And if you know the boundary conditions and the symmetry, and if you are lucky, you can solve these type of Laplace equations. So Laplace equation is again this one. And then you can have, for example, what do I mean by symmetry? I mean something very simple. So people like to solve these type of problems. Let's say a box, V1, V2, V3. So here I define this Dirichlet boundary condition for a box. And on this box I have the V1, V2, let's say V2 here, V3 here, and V1 from above. And then you want to know, for example, the potential inside or outside this box. At infinity it is 0. This is a typical type of problem. So here we have the boundary conditions, and inside this equation holds. Yes, this is the well-known definition. And then you know this very well. What do I need to do in this problem? Well, I need to use, first of all, I need to define I need to use superposition, separation of variables, but the first thing I need to say, this problem I need to use Cartesian equation. Cartesian coordinates because of this symmetry. And then if I have, for example, a problem like that, so a sphere where on top you have V1 and on top of V2, this is a spherical coordinates. If I have a problem like this, this will be cylindrical coordinates. There's some V here, let's say V1 here, and V up V0, for example, but it can be many things. Of course, and sometimes you need to think a bit what are the coordinates you need to use. So let us say you have a cone. So this is a cone the potential, this is a cone, this is a surface. So this is the blackboard and I have a cone. This cone goes to infinity upwards and there is some opening angle alpha and this potential, let's say, is V0 and this potential is V1 and you want to know the field close to this tip. These people got Nobel Prize for this geometry because this is related to scanning microscopy. So then in this case it's also spherical coordinates, which might be obvious or not, depending on you. So the first thing you need to do when you have these problems, you need to determine which set of coordinates you are using. And the second thing to do is that you need to know what a Cartesian coordinate, what a spherical coordinate, what a cylindrical, etc. Which means that I assume you know the Laplacian in all these coordinates and you can write it down and then start making some machinery. Before doing that, we will not do that. This is all in Griffith's chapter 3. You know this. This is what you need to know. You need to know these things. And if you don't, then you need to, you need to practice them. I will not I'll not solve all these problems in different set of coordinates. I assume you know how to separate variables, that you know how to construct infinite series solutions and things like that. We will discuss some examples here to emphasize the physics, but you know how to do that already. So what I want to start with is a nice, beautiful theorem before we go back to this. And I want to start, the simplest thing to do is to think about something idiotic, which is one dimension. Let us do this. If you have a complicated problem in general, the best thing to do is kill it and make it trivial. Why? Because it will take us 5 minutes to solve it, and that's 5 minutes is it's nothing compared to solve the problem in 3 dimensions in a complicated, so we might as well do it. So what is this equation in 1 dimension? It's simply this. And I want to solve it in an interval. So I have x1, x2, and x is in the middle. And what is the solution of this equation? I think everyone knows. No.
Straight line.
It's a straight line. So it's good that we are talking about 1 dimension. And it's super important that it's not a sine and cosine. Exactly that is my point. A sine and cosine in this solution would give you a minima and maxima. And that would violate some basic physics that I'm going to discuss. So the solution is ax plus b, because the second derivative of the first term is 0, the second derivative of the second term is 0. It's a second order equation. You have 2 coefficients, a and b. And a and b, how are they determined? They are determined by the boundary conditions, which are on x1 and x2. You can give me either the derivative if you want, or you can give me the values of the potential here and here. And you can easily get this thing. So the solution is terribly boring in some sense. So this is x1 and this is x2 and this is v of x, and it's a straight line, ax plus b. Fantastic, we know that from high school. So we understand this equation perfectly well, obviously. So now this straight line, where is it always? Where is it maximum and where is it its minimum? It's a trivial question. x1 or x2, it's
On the boundary for both.
either here or there. One of them, the maximum was on the boundary. Okay. Now let us start. This is mathematics. Now let us start on physics. Assuming this is a real problem, and it's not. We will soon solve this in 3 dimensions and see something similar. Let us say that this is my potential in 1 dimension. And this is caused, of course, because of maybe out here there are some charges in 1 dimension, whatever that means. And I drop a particle inside here. I put the particle here. Where will I find the particle? If you don't believe, if you have common sense, I mean, which means you assume that the particle is dissipative. Where will it be found? At the minimum. This is because this lady went to kindergarten, and if I roll this thing, it will stop, which means I lose energy assuming here that there is a friction, the minimum of the energy will go down here. I'm not saying what if this is a positive or negative charge, it could be on the other side, this doesn't matter. You'll go to the minimum. So you see in this problem, where do you go to? The particle goes to the boundary. Now we want to ask the same question in 3 dimensions. This is motivation for us to ask similar questions. What is the particle, however? The particle is a test charge that after I have the potential, I put a small test charge and it will always go to the boundary. So let us motivate this a bit more. This thing, okay, so yeah, okay, dx squared, dx. So the minima and the maxima are on the boundaries in this simple way. And I'm going to connect it to a second mathematical interesting concept. And that is the following, in this case trivial one. I want to define V average. What is V average? I'll define it, but it is the average potential. In 3 dimensions it will be not trivial, and here is going to be trivial. So what is the average potential? Average. So what I do is the following. I have this solution. So this is x1 and this is x2, and here is my point of interest, x. So it's an average around a point. I have some point in space and I want to know something like the average field around this point. I take any delta. So this is delta. So this is x plus delta. And I take a minus delta. So this is x minus delta. So, and V average I want to define as the potential at plus x plus delta. I go one step to the right, plus the potential to the left, and divide by 2. 2 is the averaging process. What is this in this case? Trivial. Ax plus delta plus b plus ax minus delta plus b divided by 2. And what is this? You see, the deltas will cancel because once you have a plus, once you have a minus, ax plus ax divided by 2. So this is ax plus b. And what is this? This is the potential. So what we see here is that the average potential, no matter what is delta, delta is not important, is equal to the potential at the point. And later I'll show you that because of this type of law, now we're going to do it in 3 dimensions. Because of this type of law, there's no minimum and maximum in the regime. But now we want to do this in 3 dimensions, which is a little bit more sophisticated. Okay, the general direction is now clear? Yes? Okay, so let us do that. I'm first just stating the law of the average. I hope you all read it in Griffiths, but I might be wrong. Most likely I'm wrong. So in 3 dimensions, how do I construct a similar law? Because our world is 3 dimensions. So I want to define it in the following way. So again, we have charges all in some locations, and I talk about a region no charge. Here there's no charge. I define, this is some reference frame, not so important. I define some point in space denoted by r in spherical coordinates. This is like my x that I had in one dimension. Now what do I do to define the average? I construct a theoretical sphere around this point. It's not a real sphere, it's a theoretical sphere with a very bad picture, but maybe you can see it, maybe not. And the radius of the sphere is r. What is r? This is what I choose. This is like the delta we had before. It can be anything you want, as long as this r is not big enough to include the charges. So inside here there are no charges. And then the law of the averages, we're going to define the average. What is the average now? It is 1 over 4 pi r squared. What is this object? You know this from high school? This is simply the surface of the sphere. So when I average over, I'm going to average over a surface of a sphere. And then when I average it, you know I need to divide by the surface in order to get a number. This is just what I'm doing here. And then you take this integral, Vr dA. I'll soon explain the meaning of this. And I do it on the surface, not of the real system, of sphere which I constructed. What does this integral mean? In a picture way, I have here my sphere of size r. I take here some delta A. I know the potential in this delta A, so I take VR times delta A here, and then I do it the same here. And I sum over all the sphere. So this is like summation over all the sphere surface. All the potentials will soon do this integral, and that's what it means. So this is not a proof, this is a definition. This is why we call it V average. It's the average over the surface of the sphere, simply. And what we are going to claim, which is pretty marvelous in my opinion, this is equal V of r. Again, what is r? R is the center of this center of the sphere. Maybe here it's better to write capital R, because you are averaging on the surface. But this is a bit misleading. It's r theta and phi. I mean, in general, I mean, it's a bit. I just write v, but it means, because it's this capital R is not with respect to the reference frame. It's with respect to the ball. So it's v r small r theta and phi. Okay, so if you want to write it like this, then this is this r. Okay, yeah, you had questions?
Yeah. You said that there is no charges here?
Inside, no, I didn't say if there's no charges, then the potential is everywhere zero by definition. What I meant is that there are no charges inside the sphere.
Ah, okay.
For example, if this law is not true, imagine you have a charge q, one charge, and then I construct my sphere here, and now I average over the sphere. What will I get the answer? The average potential will be
KQ.
K. We have 4 pi epsilon 0, but actually K is much better because it's shorter than 4 pi epsilon.
Yeah.
K times divided by K times Q divided by
R.
Capital R.
Yeah.
But what is it in the middle? What is the potential in the middle of the sphere?
Infinity.
So the law does not hold, obviously. So, and it's very simple, because where is the potential of the maximum? The maximum is here, and then when you average over the sphere, in this case, it's much less than what it's in here, no matter what is the radius. So when you have one charge inside, this law doesn't hold. But if you have no charge inside, it does hold. That's why it's not so trivial, this theorem. It's in fact very untrivial. It's deeply related. The two here, as usual, this is related to Coulomb's law. If we had something else but Coulomb's, then it will not work.
Okay, so but another charges in outside the sphere can exist.
You always have charges in these problems, always, even if you don't know them. Why? Because if there are no charges all over space, there is nothing. There's no electrostatics.
Yeah, yeah.
So there are always some charges somewhere, but we just look at a region in space. So from a practical point of view, if you understand this theorem, let's say you constructed the solution of the Laplace equation, then you go to some region in space, you calculate this, and then you calculate the charge here in the middle, and then you can test your numerical solution of the Laplace equation, whether it works or not. This should hold. So this is a way to test, if you want, the Laplace equation, but it also will give you insights into your solutions, because solutions can be complicated, but this law, after you get used to it, is simple. So it helps you understand your solution, what it means, is it wrong, is it right, and things like that. So let us now discuss, however, so this is a statement on the Laplace equation, but let us discuss a consequence, which is a related consequence, which is the significance maybe of this, and that is the following statement, the significance, and later we will prove this significance, one significance. Significance. You don't know the word? You can ask me. At least I'll teach you English. Significance. Why is this important? One of the reasons why this is important is the following claim. V r theta and phi in a region with no space has no local minima or maxima. I want to stress the word local. We will connect between these two. Maybe some of you see it already. Do you understand why these two things are the same? You start thinking about it, but soon I'll explain why they are the same. But let us discuss physics now a little bit, or physics the way I see it. Why is this obvious? Is this trivial, or is this not trivial? So what is the claim? The claim is like this. Let's say, let us start with some problems that you know. Let's say I take a sphere and I have a uniform distribution of charges on the surface. This is a kindergarten exercise, right? What is the potential inside? Constant, yes, 0. So where is is there a local minimum? The answer is no, because it's a constant. Maybe surprising, not surprising, but this is what you all know. Now I'm an experimentalist. I'm not. But let's say I want to control some electrons. So I can build, let's say I can build this boundary in an intelligent laboratory, but I can also build any shape I want in the world, anything. I can take some hammers and create it. I can also put any charge density that I want. And what will be my goal? I want to create here, let's say, a minimum, let's say, for positive charges. Why would I want to do that? That is called, what is the name of such an object if we construct it as a technology?
Faraday,
No, Faraday. It's called a trap, an electron trap. I call it, this is the way I call it, an electron trap. And why would that be important? Let's say I can put the potential, I can have a minimum here, and then, I can, let's say I will rearrange the charges, then I'll bring it maybe here. I can control the electrons. These are the electrons on your screen moving around. I claim you cannot do that with electrostatics. It's impossible. So there is no, this words means in laboratories, there is no electrostatic trap. Again, what is electrostatic trap? A place, an object that has a minimum where you don't have charges, of course, because you want to bring the other particles inside, right? So there is no such thing as an electrostatic trap. What does it mean? Maybe you need time-dependent forces, maybe you need a magnetic field. You know, magnetic field will take an electron, rotate it. It's pretty localized, you can move it around, right? Now we want to do it with an electric field, and this theorem says, no, you cannot do that. And let's see why this is not trivial. So in this case, it's trivial. This sentence is trivial. But then you say, okay, let us do the following. Let us do plus, 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 plus. And maybe here I have negative charges, for example. And then I put a positive charge inside. So based on your intuition, you might say, where is the minimum?
On the surface.
The charge is positive, but on the if the charge is
It's positive.
so it will go here, right? Okay, so then in this case, the theorem is correct. The minimum is on the surface, but it's also trivial, in my opinion. Now, I don't know what you think about this case. Let's say you have only positive charge, but with varying density. Here there's a lot of density. What do we actually say here? Where will the particle be?
The lowest density.
No, but where in space? I mean,
On the surface.
it will be on the surface. So you say intuitively you are correct. Lowest density, but is this trivial? Because if it's a charged particle, what is happening here? It's going to be very close to the other charges. I think it's not trivial. Maybe you disagree with me. Why not? It's somewhere inside. Because you are attracted, the positive guy goes to the positive one. Yeah, not to the highest density, to the lowest density, but still they are close, right? So it's not so trivial, and this is because of the long-range interaction. And the idea is, no matter how you build this device and what you do with the, let's say, only positive charges, you will not have a local minimum somewhere inside or local maximum somewhere inside. This is the meaning, and this says there's no trap in the middle of the surface. You can say, okay, I can trap them here, but that, for practical applications, is very bad, right? Because you don't want to trap them on the surface, you want to move them here, and then you can make some smiley and everyone will pay you some money. Something like that. But you can't. Okay. So this is the physical motivation to look at these type of questions. But let us now go into the see why it works. It's not so complicated.
Can I ask a question?
Yeah, sure.
This is all classical design, because if I
Yeah, all this classical. Why do you believe in quantum mechanics? Okay, you bring it me outside of my comfort zone. The first question I'll ask you, what exactly do you mean by electrostatics in quantum mechanics? Then you need to go and quantize the fields, or quantum is only the particle, but so there are many answers to this and many levels of answers. But if you take the potential that I created from the surface, and then I solve the quantum mechanical problem, this now you have one electron in this potential so created. So you are right that the wave function is not exactly on the surface, but the minimum is there. So in the ground state, and remember I added friction here. So I said if you go to the lowest energy, which you always do in practice, due to some friction mechanism, then in the classical world you'll go to the surface. And you say correctly, the surface, there will be a wave function, and it will not be exactly on the surface, but there will be some penetration, which is some length scale related to h bar. But if this object is a micron, that will be an epsilon, and the theory will not break because of that. It will break because on the surface you have a charge distribution which is never exactly uniform. There will be some places which will attract it. So my point is that in principle you are correct, but in practical you'll need to construct a really small system and a really smooth system, and then okay, you have a wave function, but it will be tunneling. So let's say in one dimension, if you have a potential like this is the minimum, and you will tunnel like this, but this scale is much shorter than anything else. This is in the ground state. Okay, so let us see what is going on. And what we do following Griffiths to prove this law is the following. Okay, first let us say that we understand this law, and let us see that there is no maximum and minimum. So to do that, I throw away all the charges that created the field, and I look at my sphere here, and I define this radius in the middle of the sphere, r. It has a size r. And then let us assume that in the sphere we have a maximum which we call V maximum. Where is the maximum? Okay, and I want to let us assume that, not in the sphere, in general, we have, let us assume we have a maximum. Where is this maximum? Again, it's somewhere where there's no charge. I claim not on the boundary. So if this is the case, I build around this maximum. So let us say that this point, the potential here is the maximum at this point. V max. So at this point you are at the maximum. And then we'll have a contradiction. Why? If this one is correct. So V average is this integral 4 pi r squared V dA, the potential dA. So I need to take, as I mentioned before, dA here and the potential here. dA here, potential here, and I need to average this. But if this guy is the maximum, what is the potential, for example, at this point? It's less than this maximum, right? So this guy is less than V max. Why? Because I integrate on the surface, and all points of the surface, by definition, that is the maximum, it's inside. These are guys on the surface, the potential is lower, right? But we know from this law that this is wrong. This is wrong. Because V average, according to the law, is V max by this construction. So I constructed it to give me V max around the maximum. This one is from the law of the averages. The R here is this point, and there is a contradiction here. You cannot have a maximum in this case, so there is no maximum. And similarly, you can do for the minimum.
אפשר שאלה? כאילו, מבחינה פיזיקלית, אם יש לך כאילו נגיד מטען, אתה כאילו מעיף לגמרי את כל המטענים?
אני לא מעיף, אני פשוט עושה את האינטגרציה sorry, I'll do the integration in a region without charges.
אבל מטענים בחוץ יכולים להשפיע לך על...
Of course, that is the whole idea here. So we have a complicated configuration of charges. This complicated configuration of charges create, in principle, a very terribly complicated potential on this sphere, which is something we don't know what it is. And then we still, no matter what this potential is, maybe we even don't know it.
Yeah.
The average over this one will give you exactly the potential here in the middle. That's the statement.
אז אם אתה אומר שאין מקסימום ומינימום בתוך הספירה, נכון? זה מה שכאילו זו...
Yeah, but this sphere, I can extend it anywhere in space, not including the charges. And then there will be no maximum everywhere. I can put, you see, this does not depend. This is V max, then I created it, and then I can make it bigger and bigger if you want. So, not including the charges, of course. Yeah.
כאילו, אבל... אוקיי, אם יש לך, נגיד סתם יש מטען מבחוץ, אז הוא כן עושה איזשהו, נגיד סתם מטען נקודתי שלילי, אז הוא עושה כאילו כזה פוטנציאל כזה, נכון? אז זאת אומרת, זה גם בתוך הספירה הדמיונית שלך, יש לך מין פוטנציאל כזה.
Sure. So if you have a potential, let's say a single particle, Q, and then I look at V, I plot only V of R, right? It decays like 1 over R. My claim is that in this, and here I'll have this, in addition you have the sphere here. You see there is no maxima and minima here inside. It's here. That's on the surface. But I took the point inside and then I do this R. I'm saying the point V. If this is the maximum of the whole potential all over, this is the top of the hill everywhere, then these guys are smaller, yeah? Yeah, this is what I'm claiming.
Okay, I get that.
Yeah, you need to think about this a little bit more. It's not totally trivial, but okay, so let us prove this theorem. It's easy to prove with a single charge, and then we use superposition. So the idea is the following. Let us define a reference frame as usual, and I want to put my charge at Q. This is the charge that is creating the fields. This is something is creating. This is a single charge, a point charge, and then this distance I'll call, of course, Z. And how will I construct my sphere? I construct it around the origin. So I construct a sphere here around the origin, and its radius is R. Now what do I need to do to prove the theorem for this case? I need to integrate over the potential over this surface, and then what will I get? Potential in the middle. That's the claim. So we have to do this integration and prove that we get the known result. We know this potential in the middle. It's given by this distance. So we know it. So let's do this. So it's a kind of strange thing. Our goal is not to find the potential here, but to claim something about this integration over the surface. So the question is like this: 4 pi epsilon 0 1 over z. That's the potential on the origin, times Q, of course. Potential on origin. Is it, question mark, 1 over 4 pi r squared, independent, of course this left side is independent of r, v of r dA. So to do that, we need to integrate over the surface, so we need to change here. I want to define, okay, I'll define it. This is R as usual. So as usual, I define a point on the sphere. This is a point on the sphere, so I have R, and I have theta, and this R is actually capital R. This is theta as usual. This is a point on the sphere. So I also have here the charge Q. So this one I'm going to call R, how do I want to call it? R tilde. So think about it like this. I have one distance here, then this distance, which is capital R, and this is Z. So I have here this triangle, Z, capital R, and this is R tilde. And actually what we are integrating over, when we're integrating over the sphere, what we are doing is we are changing this R tilde when we move along the sphere, because of course R tilde here is going to be this distance minus distance, but down here it will be, of course, something very different. So what is this R tilde? It's very simple. This is, again, what is this? This is the cosine law. We just do the cosine law. It's trivial. So we have z squared plus r squared minus 2rz cosine theta. So what is the V average? This is V average. What is V average? It is, I need to divide by 4 pi r squared. That is the surface of the sphere. Now I need to write explicitly and explain what I mean by this dA. So it's d phi, the usual angle phi, which is in this plane, in the xy plane, from 0 to 2 pi. That's the easy part of the solution. And then I need to integrate over d theta. The way I do it is I integrate over d cosine theta. But you can do that also sine d theta, that's the same thing. That is these two guys. And then what is dA? It's this and capital R squared because of the integration. So these three guys are simply dA. And now I need to write down okay, I need to have Q, of course, and then I have Z squared plus R squared. This is the distance R tilde minus 2ZR cosine theta to the power half. The power half is because we are talking here about the potential, and the potential it has this units of distance, 1 over distance.
Times K.
Yeah. Okay, so this let's do this integral. So this integral is easy. I have here this cosine theta. I need to, what will happen to this, it will be downstairs, it will go upstairs when I integrate over the theta. The integration over the phi is trivial, it just gives you 2 pi. So this is, let's write it 1 over 4 pi r squared. Then I have 2 pi, this will come from the integration over, then I have r squared, and then I have q 4 pi epsilon 0. Then I have this integration. I'm going to do it as z plus r squared minus 2z r cosine theta. But now the minus half goes into plus half. It's not downstairs. And if you understand things about this integral, then you need to, the internal derivative, you need to divide by, there's a 2 and there's a minus 2zr. This is because when you take the derivative, there's this object with respect to cosine theta, this will go outside. This half, when you take the derivative, will cancel this 2. When you do the integration, you see this by part. So, yeah. So now, okay, now you need to, let's do this. This r squared will go with this r squared, this 2 with this 4 pi. This 2 pi is going to be complicated. Let us look at this thing. Let us look first at z plus z squared r squared minus 2zr cosine theta to the half. Yeah, and here I need to put cosine theta equal 1 and cosine theta equal minus 1. So let us do this. Cosine theta equal plus 1 and cosine theta minus 1. So this guy is equal z squared plus r squared minus 2zr to the power half minus z squared plus r squared plus 2zr to the power half. But what is this guy? This is z minus r to the power 2. All this to the power half minus z plus r to the power 2. And you see that the 2 is damn important here. Again, this comes from the Coulomb eventually. And this one is z minus r, right? Because I'm taking the square, and this is minus z
minus.
plus r. So this is equal to minus 2r. This 2r will cancel this r down here.
Minus.
That's
Z
minus
minus
there, yeah. Minus z minus r.
in the end of the minus
Yeah.
z minus.
And this minus will cancel this minus. So everything is okay.
I mean that z minus r. No.
Z minus r minus z is 0, minus r
Minus, yeah.
Yeah.
Exactly.
Okay, I didn't put the parentheses. Thank you. So, if you boil up, this guy, the r will cancel out, and eventually you see this z. This z is the same as this z here,
That's correct.
and then this v average is simply equal 1 over 4 pi epsilon 0 q over z. And this makes me very happy
Okay.
for two reasons. One, I proved the theorem, and now we can go and break. That's the second reason. I proved the theorem because this is equal to this. And okay, you can say I did it for one charge, but then I used the magic word. You know it already, superposition.
Yeah.
So now I have many different charges all over the place, and I continue doing the same. And then I should get the same result. So this is the average theorem, and we discussed up to now what is more important because of the average theorem. It's very useful when you apply it to your solutions. You can check your solutions even by just looking at them. I can look at the solution of Laplace equation. If someone gives me something totally wrong, and he or she gives me some minima of the potential, I don't need to check the exam. I'm very happy. It's wrong because there is a minimum, and also the same for you. So you can use this for your advantage. I mentioned the traps, that you need something beyond electrostatics to create traps in space, magnetic fields or time-dependent electric fields. That's very important physically because trapping is very important in applications. And now we are going to have a break, and then we will start solving some simple Laplace equations, and we'll make them more and more complicated as time goes by. So now we want to discuss a bit some solutions of the Laplace equation, where again Griffith's chapter 3 will give you many more, and you'll have some in your homework, different methods, different coordinate systems, etc. So the simplest case, which is not exactly trivial, is the two-dimensional case. And I like the two-dimensional case because we want to find the potential v of x and y. I throw away z to the trash. Why is this useful for me? The potential is a plot over two-dimensional planes. So vx and y, I can plot it quite easily. While, well, it's not with my skills, but if I have to solve a problem in 3 dimensions, v, x, y, and z, the v is the 4th dimension, and then plotting it becomes a little bit hard. So 2 dimensions is very nice to show you some general ideas, and we start with the simplest case, which are Cartesian coordinates. So we have, this is the Laplacian in 2 dimension, vx and y equals 0. And then, of course, we need to define the boundary condition from which we have something which is not trivial. And the boundary condition is going to be the following. I'm going to use boundary conditions which also have this Cartesian type of symmetry. So if this is going to be x and this is y, so these are the boundary conditions, I'm going to consider a system in a stripe. This goes actually to infinity. So I want to know the vx and y inside this stripe. And that means the following thing, that the boundary conditions are given on this boundary. This boundary give you the boundary conditions. And I'm going to define it in the following way. This length of this stripe is a, some a. Then the potential here, down here, is 0. The potential up here is 0. Of course, at infinity, it's also 0. This is When I say 0, I mean usually with respect to infinity, so the potential is 0, which means I ground these plates here, and of course, if I add here 0 also, then the problem would be trivial. The solution will be 0. This comes also from the uniqueness of the solution. So if I say also here it's 0, one solution of Laplace is 0, right? Then there is a theorem in Griffith's book. If you find a solution that satisfies the boundary condition, it is a unique solution. That is your solution. So if I put it 0, 0, it satisfies the Laplace equation, 0 everywhere, that's the solution. You don't need to work anymore. Of course, we don't want to do that. Instead, over here, there is going to be a sum function of y, v0 of y, which is a boundary condition. So that's the input to the problem. If you don't give me this function v0 of y in this interval, then I cannot do anything. I will define the coordinates that this will be this actually will be point 0, so let us define it, the boundary conditions. I'm going to define a bit better. So v equals 0 when y is equal 0. So actually this is y equals 0. And when y equal a, so up here is a, and v equal v0 of y, bless you, when x is equal 0. So this point here is x equals 0. And of course v is equal 0 when x going to infinity. So these are the boundary conditions. Now the problem is well defined, and now we can solve it. And how do we do this? This is just a reminder. So what we do in general is we write a solution which is not satisfying the boundary condition at this stage. So this is a particular solution. If you want to write v particular y, y, and this is called separation of variables method. You plug it into the Laplace equation, you find an equation for this capital X, you find an equation for this capital Y. Then you apply the boundary conditions, you get some quantization, quote unquote, because of the conditions on the solutions, and all this is in Griffiths. I don't want to do this because you did it many times and you should practice yourself. And then you find the solution. I'm just going to write it, Vx and y is equal to Cn, some coefficients, exponential minus n pi x over a sine n pi y over a. And the goal here is not to derive this. You did these things many times, but just to look at the equation, the solution, and understand why it makes sense. So why does it make sense? We have here exponentials and we have sine functions. In general, maybe the solution could explode, or maybe they could be cosines instead of sines. Why is this happening? This is happening because of the second derivative here. When after you separate, the solutions are either decaying exponentials or oscillating cosines and sines. Soon I'll answer this question. It's a good question. So you are looking most likely at the sine, and then you say the sine may have a minimum and maximum. Where is the theorem that we had before? And this is precisely one of the goals of this discussion, to show that there are no maximums and minimums. So, but just by looking at the sine, no. And notice how different this is from the one-dimensional case that was a straight line. Okay? Yeah.
N runs from minus insult to
no, n
minus infinity.
No. N runs from 1 till infinity. Till infinity. So let's say you worked and you got this. Soon we're going to discuss the Cn. The Cn will of course depend on this function v0 of y. There will be. This is actually a family of solutions. But let us just look at this solution and just check it. This is what you should do always in your exams, and most students don't do it. You check the solution, and if you see that you made a mistake, then you say, oh, I made a mistake. Then I know that you made a mistake, and you understand that you make a mistake because everyone makes mistakes. But if you just give me some nonsense, for example, if I had here a plus, why would that be nonsense? Why you should?
It would explode.
Exactly. So this is back to the question on what do I sum. I sum from 1 till infinity in such a way that for large x, the potential goes to 0. So Vx and any y in the limit of x to infinity is 0, of course. And this is exactly the boundary condition that I add here. This is this 0 up here. So, you know, if you make a mistake and you sum for minus infinity, I'll give you 0 points in your exam, not because you cannot make mistakes, but because you didn't think and not exclude this possibility. So this minus makes a lot of sense. And this sign is describing the modes along this way, is again the second order. And does this satisfy the boundary condition? So the answer is yes, this is where it came from. When y is equal 0, this is sine is 0, and when y is equal a, sine n pi is also 0. So this guy gives you the boundary condition at y equals 0 and y equal a. So this, at least it makes sense, but it's an infinite sum, so maybe you don't have a good feeling what it means. The next step is to find this Cn. How is this Cn found? This is something you should know, because there are similar problems, for example, in all courses in physics, I think, but let's say quantum mechanics. So how do I calculate Cn?
Projection.
What?
Projection.
Yeah, it's mathematically it's by projection. So what he's saying, are you more mathematician than physicist? No, it's okay, I'm joking. So what we use behind this is that, for example, these signs, they form a complete basis of the problem, and we look for the orthonormal solutions to this sign, and soon we'll do that. But what does this Cn depend on? It depends on this V0 of y, right? So in quantum mechanics, we have a similar infinite sums where Cn is given by the initial condition. Here there's no time, so Cn here is given by the boundary condition. Okay? So how do I need to determine the, so I need to go to the boundary, the non-trivial boundary is x equals 0. So V0y, this is a general solution, is sum over n equal 1 till infinity, Cn, we are at x equals 0, so e to the 0 is 1, sine n pi y over a. Okay, this is this thing, and I know this thing because this is given, and soon we will give some specific example. So then the next trick, which is well known, is to use the fact that these functions, we can find an orthogonal basis. In this case, this is related to Fourier series, but this is very general. It will be the same if you have a three-dimensional spherical system, you have the YLMs, it will be also orthonormal basis, or you'll have Bessel functions in the cylindrical case. So this is something much more general than the signs, but you need this tool. When you solve things, you need a formula sheet where you have the orthogonal relations of this, for example, in this case, the signs. So what is it? It's very simple integral. It's sine pi n y over a. In this case, I put in the a just for the context of simplicity, sine pi n prime y over a dy. This is equal a over 2 delta n n prime. And you saw these type of integrals, but they are important. And for me, this is he called them projections, I call them a filter, because what we are going to do is the following. I have here an infinite sum. I'm going to multiply this function by this sine pi n prime y over a. Then each one of these signs will simply disappear unless n prime and n are the same. And then I'm left here with Cn prime, which I can call Cn. Everyone is with me? You know this, right? I don't want to, I'm just reminding you a bit. So from this orthogonality relation, I can find these Cn's by an integral. Of course, I did not say what is V0y, so I need to present the solution as an integral. So Cn by this well-known technique is 2 over a v0 of y sine n pi y over a dy. And you see these coefficients. V0 has units of potential, dy has units of length over length, so this CNs have units of potential, and that's why this has a units of potential, and this is the units that you expect. Also this I like people to check in exams. So this is the solution. Essentially, we have the solution, but did we gain a lot of insight? We gained some insight, but we didn't gain enough insight maybe. So, because it's an infinite sum, okay, so let us see what is going to happen and how do we look at this. So, for that, let us look at a specific example. Where the v0 of y is a constant. That's the simplest example I can think about. And then you have a kind of symmetry because the middle of the stripe is the same going up or going down. So immediately you know that if this is a constant, or more generally, if this is an even function, the potential here and here should be the same. On the other hand, the sign in the infinite sums of either odd or even parity. What does it mean? Mathematically, what do we expect?
The sum of the odd or even.
Right, the summations eventually will not be over all the ends, only on half of them, because of the symmetry that I impose now, additional symmetry that I impose. So if I take v0y equals simply v0, and I use this formula, I solve this integral, which is trivial. Even I can solve it because the integral of a sine is a cosine. And then you get this solution, which is given in Griffith's book, which is 4. This is, okay, the number 4 I don't think is trivial. Sorry, pi. Pi n equal 1, 3, 5 over the odd ones. This is again because of this. It's to be expected because of this symmetry that I mentioned. And then you need to have this sum 1 over n e to the minus n pi x over a sine pi n y over a. Okay, you have an explicit solution when you can all clap hands in enthusiasm. But this is not good enough, or this is one more step forward, but it doesn't show you how does it look like because it's an infinite sum, right? So, but luckily you can plot it very easily. And then you can do two things. I'm not sure this is in Griffith. I think that when I taught it the first class, I asked Mathematica, then there was no ChatGPT, what is this sum? You can ask, sum this series. This is another step that is useful, and what I find is Vxy equal the following: 2v0 pi tan minus 1 sine pi y over a divided by sinh pi x over a. Possibly both solutions look as bad as not much advantage. There is certain advantage now of this one. You can do a nice exercise if you like these type of exercises. Let us look at x equal 0 again. So what is Vx equal 0? It should be v0. If I look at this object, this is 4 pi over, 4v0 over pi, 1 over n sine pi n y over a. This is the solution, n going from on the odd. Now this is a bit strange, right? Because the right-hand side depends on y, and the left-hand side is independent of y. This is the constant potential that I did. So you can prove, how will you prove that this is independent of y? Well, you need to work a little bit, but you can prove that this infinite sum is independent of y. The way I did it, I wrote this sign as ei n pi. The imaginary part, then you have an n in an exponential, then you take the integral of that to get rid of that, then you sum an infinite number of exponentials, you get rid of the y. You can show that this is correct. So here I have an infinite sum which is equal, this infinite sum is equal pi over 4. You can show that easily. In this solution it's a bit easier. Why? After you sum the series, of course, you paid some price and then it becomes easier. If I put here x equals 0, this is sinh 0, this is 0, this is tan to the minus 1. What is this? Tan to the inverse tan of infinity? Pi over 2. Pi over 2 v0, that's the boundary condition. So in this case, it's easy to check that v0y is equal to v0 just by knowing the inverse arctan of infinity is pi over 2, then you are done. So okay, but again, maybe some of you claim I don't really understand this function, which is totally legitimate. So then you need to actually plot it, and it looks terribly boring. After you know the average theorem, and that's the way you can check things, or you can understand the physics from the starting point. So what I want to plot is that I want to plot the following. How will I plot it? Yes, this is a bit complicated because I need to plot the potential in the third dimension. So give it a little bit tilt, and this is v. This is x over a, let's say, and this is y over a. And here we have, at x equals 0, we have a constant, right? So this solution looks something like that. Very bad, very bad. How do I paint it? It's like a slide going down. Do you understand this painting? Even I don't understand it. So it's like a slide. You go down here, but you can fall down here or down here. Why? Because on this line and on this line the potential is 0. Here it's a constant, and at infinity it's a constant. And there is no minimum or maximum, so it has to go from here. Let's say I go along one line. I go from here, I go down on the slide. Like that. If I start here, I go down on the slide like that. If I go up here, it will be like a parabola. This is what you need to imagine, all this solution. This is how it looks. I hope you understand it. And you can plot it on your telephone much better than I can. So this is the solution, and it's obviously satisfying the law of minimum. But now you can ask a question. I choose a very particular boundary condition, right? What about, let's say we don't have an infinite sum. I choose the particular solution, which is given here with a specific n. Let's say n equal 1, because if the boundary condition gives you one of these solutions, you don't need an infinite sum. There's all the Cn's are 0 except for one of them. So what will happen then? Because then I'll have this sign, maybe not n equal 1, n equal 10, it will be oscillating, right? So this solution will be in this direction, you'll have these oscillations. But in that solution, that way it will be exponentially decaying. Is this a global minimum? If you go in this direction, on one of these guys, you will experience hills and valleys. That's true, but it's not a global minimum because you are decaying like this. So also for a single solution, so if I have a solution like this, n pi x over a sine pi n y over a for some specific n, let's say this is vx and y times v0, then this guy is decaying along the x direction. This guy might be oscillating, but the combined effect, which is very hard to plot, is no minimum because this is just going down, right? So if I have a cut along this one, so if this is x and y, this is y, and this is x. So I have here something oscillating. If I go in this direction, there is a minimum, but it's not a real minimum, of course, because it's going down here like that. There's no global minimum and no global maximum. So a particle that will be here will slide here or go to infinity to the. So you saw that this law gives you insights on these solutions, but you need to understand this law of averages in order to use it. Okay, so now this was a simple example. And now we want to go into spherical symmetry and 3 dimensions. And so what in spherical, if you have a Laplace equation with spherical symmetry, of course you use spherical coordinates, but what is the name of the special functions? Here it was sines and exponentials. What will it be in 3 dimensions? In spherical coordinates? What is the name of the special function that replace sines and cosines and exponentials? Spherical harmonics. And let's say I have also a phi symmetry. Spherical harmonics are built of Legendre. Okay, so my goal is to show that the Legendre solution is only part of the solution, so that will be a little bit more intelligent than the usual thing. So if I have a spherical problem, let's say something like this, V1 and V2, for example, then I need to show Laplace, and it's given by this 1 over r squared d over dr. I'm just writing the Laplacian, dv dr plus 1 over r squared sine theta d over d theta sine theta dv over d theta plus 1 over r squared sine squared theta dv d phi squared equals 0. So this is pretty awful. And also notice that because this is the Laplacian, this 1 over r squared is actually not important. I mean, that's just the definition of the Laplacian. But in other problems in physics, it is important because then the Laplacian of something is equal to something, and then you cannot cancel this 1 over r squared, but here you can actually cancel it out in Laplace. So what do you do in this case? So now we are going to assume for simplicity azimuthal symmetry. This is an example of azimuthal symmetry. It means that we are talking about the sphere, and then the angle phi is not important. So no dependence on phi. So what I'm doing by this, I'm simplifying things. I'm actually going from 3 coordinates to 2 coordinates. The coordinates are theta and phi. And of course, as usual, I think you know this is theta, and we have here phi, and this is r, the usual coordinates. Okay, then what you do, again a reminder, Vr and theta, you write it as a function of r. This is the separation of variables method. Two functions which are now defined, capital R and capital theta. So here you have two lines. This is the function and this is the variable, capital R and R. So then when you put it in, this is again a reminder, I get the following d over r squared dv over dr plus 1 over sine theta d over d theta sine theta dv over d theta. This is equal 0. And then what do you say? What is this guy? What is the usual name? No. Okay, so now you have this. Okay, now what you do, you plug in this and then you divide by capital R times this theta. So this is divide. And then this guy will be independent. It will depend only on theta. This guy will depend only on R. So after division depends only on R. And this depends only on V, on theta. And if this depends only on theta, this depends only on R, and it's valid for every R and any theta, this is going to be some constant. And the constant will be called LL plus 1. This is what the usual notation. So what we find after doing that well-known trick, 1 over R, this comes from after you divide, you get this one, you get d over the r squared dr over dr equal LL plus 1. And then you have another equation from this part, which is this 1 over sine theta. I'm going to multiply by the LL minus 1, and then I'm going to have the following equation, d over d theta sine theta d theta d theta. That is equal minus LL plus 1. The minus is because you need to take it to the other side. Then this multiplied by sine theta. This sine theta comes from this sine theta. I'm not showing you every step because you saw this many times, I believe. And you have here two equations for this capital R and the capital theta. And you need to solve them. And these are well-known problems. So let us write down the solution. So for the what is R of R? It is some constant R to the power L, generally A of L, and this B RL plus 1. So this is the solution describing how one node, this is the capital R, is increasing with L, with R, or decreasing with R. L is going to be greater or equal to 0. It's quantized. I'm not proving this, but this is well known. So for example, if we go a little bit back to physics, when we will work inside the sphere, I have here two coefficients. Which one of them, there's no charges inside the sphere, which one of them will be 0 and which one will not be? A will be something and B will be 0 inside because you don't want to diverge. When you work outside, potential is far away is 0, and then you'll do the opposite. That is, the solutions are decaying. So these are decaying solutions, these are increasing. This can be inside the object, this can be outside the object. So we solve the problem, in the example, this problem here and here separately, and the goal is to determine these guys. What is this theta? It's also a well-known equation. This theta I'm not solving it here, is simply the polynomial of Legendre cosine theta. This is very weird, however. Later you'll see that this is sometimes wrong. So this is what you learned. I'm actually starting now the lesson. Up to now it was a reminder, and this is what you know. This is the polynomial Legendre. It satisfies this equation. It's an eigenfunction equation. This is the eigenfunction, eigenvalue. No, not exactly eigenvalue equation, because it satisfies this equation. And what is PL of x? PL of x. So x is cosine theta. So this is L. So if L is equal to 1, 0, 1, 2, for example. If it's 0, what is it? It's 1, and if it's 1, it is cosine, and then it is something like 3x minus 1 over 2. And you have formulas for all these polynomials. You have the Rodriguez formula that gives you all these polynomials. We know everything. We know everything about this already from quantum mechanics and a few other courses, so we know this. And essentially we are done, because now we have the basis and we can construct the basis. So if you look at Griffiths, what is the solution? In general, I'm not talking here about a specific system. I'm talking about a system with spherical symmetry and no azimuthal dependence. So what is the solution? It's something like this. Sum over L going from 0 to infinity. So before we summed over n, and now we sum over L. And this is given by AL r to the power L plus BL RL plus 1 PL cosine theta. And then you have two sets of infinite numbers, ALs and BLs, and we need to determine them. And how are they determined? By the boundary. And what is the tool? An orthogonality relation, like with the signs, it's the same thing. So you need an orthogonality relation. So let us say, for example, we want to solve a problem inside the sphere. So we have a sphere, we have some potential on the sphere. It doesn't have to be V1. There is a symmetry, there's no phi dependence on the boundary conditions, but it's something very general still. So on the sphere, we have some V capital R. This is the sphere, which is a function of theta only. This is the boundary condition, and I solve inside the sphere. This means the BLs are 0. No divergence. Divergence, what would it mean, divergence like 1 over r? It would mean that there is a charge inside physically. It also would mean that the maximum is in the middle, and we know that the maximum is not existing, so it's obviously wrong. So this is the reason why we can just throw all of them away. Now, so the solution is VR and theta. So this one is on the boundary, on the sphere. This one, r, is less than the size of the radius, which is capital R. So this is simply a sum, L from 0 to infinity, AL, RL, PL cosine theta. Hallelujah. Now I need to determine these ALs, and I do it with an orthogonality relation, which in this case is the following. I again look it up in a textbook, cosine theta. I take the polynomial Legendre with L and L prime. I go to my formula sheet. sine theta d theta, which is d cosine theta, integral from 0 to pi. This one is equal 0 if L is not equal L prime. This is like the delta Kronecker that we had before. And here the normalization is a bit different. It's 2L plus 1. So if you want, you just multiply this by the other side. It's 2L plus 1 over 2, and then you'll get the delta Kronecker. So this is when L is equal L prime. So this just states how these two functions are orthogonal one to another. When you have different L's, it gives you 0, and when these L and L prime is the same, it gives you the same. And then with this, like before in many courses, I can find AL. I think you understand this. I'm just reminding you. So then I just do this integral. And I find these ALs, and then I'm done. With this very technical method. So I need to multiply this on the other side, and what will I have here? I will not have this function. I use the boundary condition. So the boundary condition is V R theta, something that is known on the boundary. I just need to plug in some AL R to the power L, but now it's capital R because I'm on the boundary. PL cosine theta, L from 0 to infinity. I multiply this function with PL prime on the other side. I do the integration on cosine theta. I'm left with only AL RL using my filter with this equation. So what is AL? I do this simple math. It's 2L plus 1 over 2 to the power RL. This comes from here, which came from here, times integral from 0 to pi, PL cosine theta, VR, which is given, theta sinus theta d theta, and that's it. That's the solution in a formal way. If we already did this, let us do one example, which at the beginning looks complicated, but eventually it will turn out to be easy. Let's assume VR theta is some constant, which has units of potential, sinus squared theta over 2. So what we have here, we have a sphere. We are looking inside. We're looking at the potential field inside. And the potential on the sphere has this strange shape. Up here, what is up here? Theta is equal to 0 up here. So sine 0 is 0. Here it is C over 2. Because then you are at pi over 2. This is pi over 4. This will be square root of 2 over 2 squared. That will give you this half. And here it is C, etc. So this is the potential on the surface. And now we want to calculate the field inside with this very strange potential that, let's say, some guy measured and he gives it to us. And then we want to say, what is the field, electric field inside? So what is the trick here? What is the trick you suggest to, I mean, you can be smart or...
This is the Legendre polynomial.
Yeah, the first thing to do if you have a function which is a little bit complicated but not too complicated is let us put this one as a linear combination of Legendre polynomials. Why? Because then I can use the orthogonality relation, and then here I'll have a sum of, let's say, 1 or 2 or 3 polynomial Legendres, and then these integrals will become trivial, some of them, because of this integral. So that's the trick. That's the very simple trick. And what do you see here when you see sine squared? What do you see?
זהות של כזה חצי זווית.
Yeah, so we need to write it as in the following way. So this I want to claim, I'll assume you'll all see why. This is P0 cosine theta minus P1 cosine theta. And while here I had theta over 2, here I have theta, and here I'm using, this one is simply 1, this is simply, so this is 1 minus cosine theta. And then I'm using a simple identity for cosinus of 2 times alpha gives you cosinus squared minus sinus squared, and 1 minus sinus squared will give you this, 1 minus cosine squared will give you this sine square, and this will give you the 2 when you do things a little bit carefully. And then I'm essentially done, because again I go back to this equation and I can do these integrals for AL. So solving for AL, what do I learn from here? What L's are important? These are these L's, the 0 and the 1. Are non-vanishing. And again, if you have some person who doesn't know these small tricks, it's a problem, because then you don't know this function. Let's say L equal 20, you don't know this function. So okay, so then in the middle of the exam you'll calculate L equal 20, you don't have time. So you need to do these type of tricks in order to find this AL in a reasonable amount of time. So only L equals 0, this is this 0 and this 1 are important in this solution. And then instead of an infinite sum, I have only 2 terms. Then if I do this, I immediately get VR and theta. This you can do the exercise till the bitter end. It's 2 lines of algebra, which is given by this C over 2, 1 minus R over R cosine theta, and that's it. That's the solution. After all, from the L equal 1, I have an R. This is this R. Of course, C as units of potential, then this is why you have R over R, capital R. This is related to the fact that A1 has 1 over R. So this makes sense. The cosine theta is the polynomial Legendre 1, and the constant is polynomial Legendre of order 0. Okay, but what does this crazy potential mean? What is this what is the field now inside the sphere? Anyone wants to guess? I wouldn't. First of all, it's easy to take this solution and prove that the average theorem works. So what you can do quite easily. Let us take R to be capital R. Then you integrate over the sphere, and that will give you the solution inside. This is very easy to check. I'm not going to do this. But let us look at the field. So what is the field? So up till now we used spherical coordinates, and the tendency of people is to continue with the same coordinates that they're using. Also, the same is true for myself. So let us calculate this with the spherical coordinates. It's easy. You know the divergence, and you get an expression which is, I don't think so nice, but maybe you think otherwise. R, so this is a vector in the R direction, minus C over R over 2R sine theta theta. So this is R and this is theta. These are the two directions, R hat and theta hat. What is this? sphere. This is something simple, and the hint is in here. Let's look, what is written here? It's in front of you.
1 minus z over
Exactly. So the trick to understand this one, of course you can take this and then you can transform it to Cartesian coordinates, but you can also look at this solution, and that is v, which is a function of z only. The z of the Cartesian coordinates is c over 2, 1 minus z over r. Because r cosine theta is z. Right? If z is r cosine theta. Now we have a very simple potential because it's just increasing inside the sphere. Now, what is the derivative of this? What is the divergence of this? Even I know how to do that because it's going to be a constant. And in which direction? In the z direction. So what is the field in this unit? In this set of coordinates, it's simply c over 2r in the z direction. So we have here a crazy charge distribution given by the sine to the power 2 theta over 2 law. This is the potential, goes like that. And then the field inside is simply a constant, independent of nothing, independent of z, and of course it satisfies the, I mean, where is the maximum? On the surface, obviously. This is clear. So this was an example where the method works, and now I want to give you an example where the method doesn't work. It's not in Griffith, so it's a bit more interesting. What is the time now? 11:06. So please wake up, because now something interesting, I think, is going to happen. Sometimes there are problems in these type of methods. And try to catch this when I do it. What is the problem? I'm going to solve a less trivial problem, reach a contradiction, and then solve the problem in a different way. So now I want to solve this problem, which I'm going to define like this. It's related to something called scanning tunneling microscope. So the scanning tunneling microscope, I have a surface. Let's say this surface. I bring a tip very close to it. There's tunneling, which means the effect is really quantum mechanics. But the first order approximation is that this tip has some potential on it, and the surface has a potential on it. And you want to calculate something simple. What is the electric field close to this tip? So you have something very narrow. It's coming to this surface. There's difference of potential. So close to this tip, there will be a very strong field because there's a gradient. And why is it important to have a tip? If this tip is narrow enough, and if you use some tricks from quantum mechanics, you can measure the scale of the surface on the surface of atoms and go to Nobel Prize. But that is due to tunneling. That's why you want it to be very, very sharp. That's trivial. If I measure you and I average over you on a scale like this, I don't see anything. I need to see the small scale, so I need a very narrow tip. So we are going to solve. We are not going to get a Nobel Prize. That will be next lesson. We are going to solve this problem of the scanning microscope in the following way. So we have this square is a surface which I want to put it in a potential that will be 0. This is a cone. It touches the, we're going to put it on the surface. You can imagine it's very close to the surface. If you put it on the surface, in reality the tip will break. That's one of the biggest problems in the scanning tunneling microscopes, but we put it on the surface, and this is a cone. Hope you know what's a cone. There is an opening angle which is called alpha. Alpha is some parameter that we put into this problem, and the potential here is, I call it V0. So this object also has a constant potential on it, And that's why if I come, for example, here I have V0, here V, and then there will be a potential drop, which means that there is a strong electric field here, close to this tip. This is obvious. This cone itself, it looks like an ice cream cone. That's what I mean by cone. So you just open the angle and then you rotate it, and you'll have this cone open. And this is the geometry that we are looking at. And what is the question? The question is, what is the field inside and what is it outside? The potential. What is it inside and then what is it outside? What is it inside? Actually, it's a trivial problem inside. Inside, which means in this region here, inside the cone. What is it? Good. So V is equal V naught. Why? Inside the cone, there's no charge. Laplace equation holds. Laplace equation holds inside. What are the boundary conditions? Only the cone. He doesn't see the plane here. If I take in Laplace equation a constant, does it satisfy the equation?
Yes.
Yes. Does it satisfy the boundary conditions? Yes. Now I come from my friend, the mathematician. He told me that it's unique solution. I'm done. So inside, because the Laplacian of V0 is 0 and boundary conditions satisfied. So I'm very happy. It's very easy to solve it out inside, but outside, is it easy? No, not so easy. This is what we are after for. So now we go. All of you read Griffiths, of course, and what do we need to do? First of all, we need to say what is the symmetry here. So I put the reference frame here, and I have R going in this direction. And I see that the phi, the angle, the azimuthal symmetry is not playing a role here. Why? Because the cone, this is because when you eat an ice cream, you immediately see that there is symmetry of this phi here. So the solution here, what do we know? It's a function in general of R and theta only. And that's very good. We don't have these YLMs. No, we don't have spherical harmonics. What do we have here? Legendre polynomials and the solution that we just gave now. So we can just use the same thing, right? It's very easy. In principle, it's easy. So if we are looking at the textbooks and not thinking too much, the solution is this. The sum over AL RL. This was before. I showed you this is the general solution. PL cosine theta like before, but now we need to solve and find what are these ALs and what are these solutions. So now let us think. Let's say I work here, I go to infinity with this R. This is R, very big R. What is the potential? 0, right? So we are, in some sense, we are outside this thing. So what do we know? AL is equal to 0 since V at infinity 0. Okay, good. So now where shall we look? This is when I look at R to infinity. What is the other easy point? Let us look at R small. So if R is small, what will we get? So assuming that the solution is not diverging, R equals 0. So I come here close. Why is it not diverging? Because you have V equals 0 and V0. V0 is a finite number. V is a finite number. So nothing diverges here. So at R equal to 0, the potential is not diverging. This is only my, I don't say what it is. It's not, but it's not infinite. That's all, because of the boundary conditions here. So what does it mean on the BLs? Can BL be, let's say BL can be some number. It has to be 0, except for?
L minus 1, not
Equal to 0.
y 1.
Wait. Wait, did I get mixed up with the L's here?
What about L0?
Yeah, but okay, so, but it's a problem anyway. I mean, it's simply a problem because all of them, all the BLs have to be also 0. And then it's all nonsense, right? You agree that it's a contradiction, right? I mean, we can't solve this problem. I just want to check that I didn't make a mistake here. Okay, so sorry, here I made one mistake.
Yeah.
Here L not
zero.
equal 0.
Yeah, exactly.
Why? L equals 0 is not a problem. Why do we say it's not a problem? It doesn't
It's
diverge at
constant.
infinity and it doesn't diverge at 0. So what is the solution according to this? V, R, and theta.
Some kind of constant.
Only L equals 0, so A0, P0, cosine theta. But what is P0 cosine theta? 1. So this is A0. What is this?
Constant.
No, it's not constant, it's nonsense. Right? Because if the solution is a constant, okay, the boundary conditions are not held, but there's no physics. I mean, there's nothing. So what went wrong? What did I do wrong?
We solved a similar problem in X3 and we used Green's function. Or something like that.
Okay, good for you.
No, but and then it's worked.
For this problem.
Something similar.
Yeah, but you can use green function if the. First of all, let me give you. There is a solution to this problem, and if there is a solution to this problem, you can solve it in many ways. We'll talk about green function a little bit next lesson when we solve Poisson. But when I say what is the problem with this equation is in Griffiths, and you were taught these equations. Okay, sometimes you don't have PL cosine theta, you have the spherical harmonics, YLM, but that just makes it more complicated. What is wrong here? So, okay, it's not so trivial, but what is wrong here is that you see there is not only one Legendre polynomial in some sense. And when you think about Legendre polynomials, it's very strange. Because what do we say? We have some equation. What order is it? It's second order. It's second order. Why do we have one type of solution? You know, usually you have two types of solution, like cosines and sines and things like that. Here we just took one of them. So the idea is that in this example, the polynomial of Legendre is not enough. You need to think more. There are some hidden polynomial of Legendre that usually physicists don't talk about. What is the letter coming? What comes after P? No, Q. So these functions are called QLs, and they are important. And why do we usually throw them away? Why do you want what? No, not because of that. I mean, if they describe the truth, then the truth can be hard, I know this, but you need to face reality. Why do we throw them? Can anyone guess why do we usually not use them? Physical, yeah, I mean, physical. Whatever method. Something to do, exactly. So, usually we throw these functions away because they diverge somewhere. Very good. Where do they diverge in this type of problems?
In the origin?
What is the origin here? Not R. The polynomial Legendre depends on theta, right? So
on the surface.
No, they diverge on theta equals 0. So what is going to happen here? You have some functions that will diverge when theta is 0. But in this problem, it's not part of the problem because theta has to be bigger than alpha. So the function, if you will continue them in an idiotic way, in a wrong way, they will diverge, but you are protected by this geometry. And in this case, polynomial Legendre is not enough. You need to go from P to Q. This is what we're going to do, okay? But that's the general story. We need to go back to the basics. We are not going to solve all the Q's. We are lucky because this problem is very simple. You don't need green functions. You can solve it quite easily, in fact. So I'm happy you solved it in the past with green functions, and now we'll solve it in an easy way. I think it's easier than green functions, but okay, this is a matter of taste. So let us see how you do this. What do we need to go? We need to go back to the blackboard and look at the equation for theta. So this is why I did all this separation of variables. In the separation of variables, I said V, R, and theta. Remember, there's no phi because of symmetry. Only two coordinates, thank goodness. This was equal to this capital R and then this big theta of theta. And we wrote down the equation for capital R. That will remain the same thing. Nothing will change. But now we are going to remind ourselves, it was in your notebooks a minute ago, it was given by this equation. That's the reason I gave it to you, even though you saw it several times in your life. And then this is capital theta, d theta, minus L plus 1, sine theta. I arranged it a little bit. This is the famous equation behind the Legendre polynomials. So, for example, if L is equal 0, then this one can be a constant, and it all obviously satisfies the equation. So what we are going to do now is, okay, let us do a trick. Let us multiply this by sine theta d over d theta and divide by sine theta. So sine theta divided by sine theta is 1. Here I have sine theta, and here I'll do the same thing, squared over sine theta, d theta equal, and now I'm going to take the simplest case, L equals 0. My claim is that L equals 0 is going to solve me all the problem. You had a hint about this. Why? Because you saw that mathematically, not satisfying the boundary condition, P0 was enough. But what we will do now, we will start from the beginning, and what you do at the beginning, you say L equals 0, and in this problem it's simple, so eventually this will give you the solution. You don't need to go too deep into these Q polynomials of Legendre. Now let us look at this equation. So the idea, the reason why I divided and multiplied by sine theta is that here I have this guy and here I have this guy. So what is this? This sine theta I can wipe out because L equals 0, so I can kill this one. What is this sine theta d theta? What I'm going to do, this is the usual trick. I'm going to write this as x equal cosine theta, because this is also the way these French mathematicians thought about these problems. They didn't have the sines and cosines, they had this x. And then dx is, in absolute value, sine theta d theta. So this sine theta d theta is simply, when you transform it, is dx. And what is sine squared? It's 1 minus x squared. So I get this equation with this definition, d over dx, and now this function, which is a function now of x, equals 0. L is 0, so this is a equals 0. So what is the solution of this equation? The solution of this equation I'm going to write with this Q. I'll write down the solution and then we'll check it. It's 1/2 log 1 minus x, 1 plus x, plus d, some constant. The d constant is like the usual polynomial Legendre, which is a constant. You can also have a constant here because this equation is linear. This solution, as I mentioned already, what happens to Q0 when x is 1?
It goes to minus infinity.
1 minus 1 is 0. Log of infinity is diverges. What is x going to 1? Theta equals 0. It's inside the region, which is okay. This, I'm telling you the trick. But this is the reason why you throw this away, and the polynomial Legendre is not this, it's this. In the usual case, because this is bad, so the constant here will be 0, you throw it away. But now we are not allowed to throw it away. Let us show that this is the solution. So what we need to do, let us take the derivative of this log 1 minus x, 1 plus x. So now I'm just checking that it satisfies the equation. So this is d over dx log of 1 minus x minus log of 1 plus x. This is because you have a log of a ratio. This one, I take the derivative. This is 1 minus x. Internal derivative is a minus, but so so I have minus 1 here, and here I have minus 1 plus x. Where did I make a mistake? I made a mistake here. Sorry, this is a mistake. Yes. This is a plus and this is a minus. My conclusion before is the same, but because it doesn't matter if it comes from the above or not. So let me fix it here. Minus. This is a plus, this is a plus, this is a minus, minus. Then this is 1 minus x squared. When I join them together, this is 1 minus x. And this is 1. This has to be a plus, sorry. Yeah, because when I take the derivative from the internal derivative, I have a minus and a minus, this gives you a plus. And then this gives you 1 plus x, 1 minus x, this gives you 2. And why is this important? Because this is this function here. This is 1 over 1 minus x squared, it's the same as this one. So what we get is d over dx, 1 minus x squared d dx, of this log of 1 plus x, 1 minus x. The constant now is not important. This is equal 0. So this is an easy exercise. So now what we do, so what is the solution? It's this logarithmic function. But now we need to...
יש כאילו קיו גם לאלים שהם לא אפס?
Yeah, there are more of these Q's. There's a whole family if you look it up in Wikipedia. But in this problem, we just need the L equals 0 case. So this problem is a simple problem. And then what is the solution? So the solution, VR and theta, I translate this back to cosine. And I can write the solution. It's something like C log 1 plus cosine theta 1 minus cosine theta. This is this minus. Now I didn't make a mistake.
That's all.
Actually, that's all, but in principle you can say plus d,
Yeah.
but we already canceled this d. That was the constant that we had before. From the boundary conditions, d is equal 0. But we need to determine this c. But this is given by this v0. So the solution is simply, if I plug in here, first of all, there's something strange about this solution. It is independent of small r. It depends only on the angle, right? So there's no r dependence. It appears r here, but there's no r. And this is because we took only the L equals 0. That's the mathematical reason. The fact that it doesn't depend on r doesn't mean that the fields are independent of r. The fields will depend strongly on r, even though the potential is independent of r. When we take the divergence. And this is the physics, because the physics says the electric fields here are big. They will come soon. So what is this constant? I'll just write the solution. The constant can be easily determined. And this is the final solution. It's V0 log 1 minus cosine theta 1 minus cosine theta divided by what?
The same just with alpha.
Exactly. Cosine alpha 1 minus cosine alpha. This is a beautiful solution. Because you see, when I plug in theta equal alpha,
It will be the
this is
V0.
1 over 1. That will give you V0, which is the boundary condition that I applied. So this solution can be simplified a little bit. So first of all, we write V of theta. There's no R here. That's a surprise. Then you have log of tangents of theta over 2 over log of tangents alpha over 2. This is useful. I mean, it's not really useful, but it's a little bit more elegant to write it like this. So, for example, what happens when theta is pi over 2? This is something you should always check. Theta is pi over 2. What is tangents pi over 2? That, or cosine, that will give you 1. Log of 1 is 0. What is this 0? This is the potential in the plate here. So we can easily check the final solution. Does it satisfy the two boundary conditions? It does. Okay, if you had time, you could take this equation, plug it into the Laplace equation, and check that it is a solution. And if it satisfies boundary conditions and it is a solution, it is a solution. That's it. There's no argument about that. And the only last thing I want to point out in the remaining minute is the following: this strange thing that this does not depend on R. The reason why it doesn't depend on R is that there is no length scale here. What is the length scales here? There's an opening angle alpha, but there's no size. Unlike the size, let's say we have a problem, size of a sphere, size of a box, and some potential. The cone is infinite, so there is no typical size in this problem. What I'm trying to say is the opposite, that if you had a box of length L, if you have a sphere of radius R, the order of magnitude of the fields, at least, are determined by these length scales. Now, these length scales are constants. So they have to appear in the potential. Then when you make the derivative with respect to R, which is the real space, they will appear there. So if you have a finite object, you always expect some dependence on some length scale, and then on R, because you cannot construct R as to, V is 0, but with what will you scale R? It has to be scaled with some length scale, but there's no length scale. This is the reason why it's independent of R, but the field is dependent of R.
How can you say that the cone is infinite and the potential at infinity is zero? It doesn't make sense.
It depends which infinity. Okay, so this is valid, of course, I mentioned this before, this is valid for theta greater than alpha, right? This is outside. Inside, I mentioned this already, VR and theta is simply this V0, very boring solution. So when I say infinity, what do I mean? I mean, you have outside the cone, like here in infinity. Yeah, because this solution is only valid inside the cone. This is outside. This is theta less than alpha. We don't care what happens inside for obvious reasons. We cannot go inside the cone usually unless we fill it with ice cream and then we eat it. So what is E? Again, outside, minus R d over d theta v theta theta. Of course, there are other terms here, but I need only the theta term because the function here does not depend on R, so I don't have the R term. This is for the specific example. And here you can see immediately the direction of the... So if this is some theta, and you have a point here, this is this theta going down. You also see from this equation, without taking the derivative, what is the R dependent? It's simply 1 over R. And what does it mean? And what the 1 over R means that if I'm coming close, the field is large, of course. It's not like a Coulomb field, which goes like 1 over R to the power 2. It goes like 1 over R. Which is similar to what? What other object gives you 1 over R? An infinite wire also gives you 1 over R. But this is a different, because this is with an angle that turns like this, eventually going down. So the E, if I take the integral, take the derivative, is minus V0 ln tangents alpha over 2. Here is the alpha, 1 over R theta. Okay, so what we saw here is one example.
What about the partial derivative of dependent on theta?
Here is the partial derivative.
Yeah, but you didn't
Oh, I did it a long time ago. That's a good question. Let me check. Yeah, my mistake. Horrible mistake. You should fire me. No,
This one. Oh, that's annoying.
yeah, this is, I copied it. That's why. Sine theta. Thank you very much. It's important. Remember that it's sine theta, but the theta equals 0 is not here, because so this does not diverge. The sine theta doesn't diverge. So, of course, you're right. Okay, so what we saw here is an example where we cannot use, or we cannot always trust the well-known polynomial solution. This cone is not found in Mr. Griffith's book. So the idea of this lesson was to give you towards the end of this. You need to know Griffiths perfectly, but you should not trust him. I think Griffiths is an excellent guy. He also mentions this, but he mentions this in one line, and we solved it, which will hopefully put it into your head a long time from now. The whole problem came, or the whole strange thing came, is that you have a second order equation and you should have two types of polynomials, PL and and QL. Usually the QLs are gone to the trash, but not always. So what we will start next session, I think next week we have a lesson. After Pesach, we will solve some cylindrical problems, which are. I believe these problems are known to you because usually people use these YLMs, but I think the Bessel functions, you heard about them, but we will go a little bit deeper into this when you have cylindrical coordinates, and then we'll do very simple problems with green functions, and then we'll move on to the case where we are using electromagnetic fields in matter when we have polarization and all these problems. This will be after Pesach, so I wish you happy holidays and enjoy your vacation.
Thank you.
Oh my God, it's so